Hi, welcome to this talk about Git, explaining the black box. First, why this talk? Well, Git is one of our basic tools of the trade. We use it often, probably multiple times every day, and because of it doesn't change that rapidly, so it's a great investment to learn some more about this tool. So, a small disclaimer, this talk won't be about how to use Git. There are plenty of talks about that. This is not a talk. This talk won't be technically correct. I will use some creative freedom to explain how Git does things. So it's not a perfect representation of the Git architecture, but it's more a conceptual view to give you some more insight in how Git works. And I really want to urge you to listen carefully, even with the basic stuff like commits and branches, because you will need that basic understanding for when I dive into the deeper stuff like Bisect and Rebase. So now more into depth, what is a commit? Well, a commit is a snapshot of your project or your files in your folders. Specifically, it's a snapshot of your project of a specific moment in time. So for instance, you have these two files and then you add a folder with two more files. And then the commit will be you've added two files in the folder source and you've changed or you added some text in the existing file. So a commit is even more specific. It's only the difference between the current state and the previous commit. So conceptually, a commit is an object with the following content, the difference relative to the previous commit, and we will call that the delta. For instance, you have a file with the text A here at the bottom, and in the next commit, the same file has the text AB, so the delta will be plus B. That's the only thing the commit will contain. It won't contain the whole content of the file, and it will only contain the difference. That's why Git repositories can be so small compared to something like SVN. So for instance, you have a chain of commits like this. So you start with plus H, then you have an A plus A, a plus L, and a plus O, and then remove the A and add the E. So you end up with a file containing hello. And it's very detailed. A commit will include line numbers and such. So for instance, a commit could contain something like this, showing what files were changed and on what line numbers. As you can see in line 189, Git sees the change of BAR to BAZ as two different changes. It won't detect character changes, but see them as a whole line being changed. But a commit has more information. It also has the author, so who committed it, what's the name and the email address of that person, and what was the date and time. And this is very important to realize that the date and time are also included. You will see why in a few slides ahead. So to simplify, you can write it like this. A commit is like an object holding a delta, which is another object containing all the changes. And it has some meta information like the author name and email, and it has a date and a time. And it also has a reference to the parent, the previous commit. Because how could he otherwise know what the end state should be? So, but what is this ID based on? And well, this is probably the most important thing of this whole talk. So if you haven't been paying attention, pay attention now, because how is this ID constructed? Well, the ID is constructed, it's a SHA hash that is created of all the information in the commit object. So the delta with the meta information, so the author, the date, and the parent are all used to create the SHA hash. And that hash will be used as the ID for the commit. So in the end, every commit hash is based on all the previous commits. So, quick in-between test. If the end result of a file is based on a chain of commits, does the order of the commits matter? Will a different order of commits give exactly the same end result? So the question is, from the example on the right, could we swap the order of the two pink commits and will the end state be the same? Well, I give you a few seconds to think about this. Okay, let's give the answer. Well, the end result will kind of be the same, because the file in the working copy will be exactly the same. In the end, we will have a file containing hello. Okay, the in-between commits will be different, of course, but the commits also won't be exactly the same. And I give you 5 more seconds to think about why they aren't exactly the same. Exact the order of the differences. And the answer I will present to you now. If you look at the commits and kind of ignore the file changes are not the same, you notice that the first 2 commits are the same on both sides, because their delta and their parent IDs are exactly the same. But the moment we put a different delta in a commit, the generated SHA will be different, because the delta is different. So therefore every following commit will be different, because every commit has a reference to its parent. But when the SHA is different, the ID will be different, and this will cascade all the way up until the last commit. So in the end result will be the same, but the IDs will be completely different. So for Git, this is a completely different commit than the other one. So to summarize, a commit contains the difference relative to the previous commit, the delta, and some meta information like the author, the date, and the reference to the parent commit. And it's very important to understand that a commit is a combination of this all. And please remember also the cascading example I just showed. So these chains of commits we call a branch. And let's call the default branch the main branch. So branches. Well, a branch, it's just a simple label, just a string. And this is a label pointing to a commit. And the only special ability of this label is that it will move when you add a new commit. So it will point to the new commit instead. So it moves. That's it. Nothing more than a label pointing to a commit. You can have multiple labels pointing to the same commit. All I care, you create 100 labels or branches pointing to the same commit. And that's also an important thing to realize, that creating branches doesn't cost anything. You can just add them, remove them. You could even remove the default main or master branch. It has no special meaning or anything for Git. It's just the default label Git creates and everybody is using. But it's still just a simple string pointing to a commit. So if you have multiple branches pointing to the same commit, how does Git know what branch to move when you do a new commit? Well, that leads us to the next thing, the head. So the head is a system label that points to a specific commit. So indirectly it points to a commit, since it points to a branch and a branch points to a commit. And the head is what branch you see in your working copy. So the head is also what moves around when you switch between branches. So if you do check out a branch, you move the head. So next up, working with branches. Let's say we have some commits and a branch named main. So we create a new branch called feature awesome, which will be another label pointing to the same commit. Then we will check out this branch, so our head moves from main to feature. And then we will add another file, commit that, and our head and branch will move with the new commit. So we add another commit and end up like this. And this is the way we often visualize it, with an actual branching away from the main branch. But you could also put it like this, just a straight commit chain, where main points to an earlier commit. And visualizing it like this helps to understand what happens when we want to merge our feature changes back into main. And that's the phrase we use often, that we want to merge feature into main, but if we do a git merge, Git kind of does it the other way around. Well, let me explain. We first do a checkout of main. So our head moves back to main. And then we say git merge feature awesome. That's what we are saying, but what Git hears is, I want the current branch to have the commits of the feature, of where the feature is pointing to. And since this is a straight commit chain, Git knows that it can just easily walk up the commit chain and then point to the same commit to, well, fulfill your wish. So that is what a fast forward means. It just moves the branch pointer to the same commit as the other branch pointer. So, but what happens when you can't just easily move the branch forward? That's where the merges come into play. So let's picture the same starting situation. We have a branch called main. We create a new branch, do a checkout so the head moves, and we add 2 commits. And then we go back to the main and we do a commit there as well. So if we now do a git merge with feature awesome, Git can't just move the main branch to the same commit as feature awesome, because then we will lose this commit. And because the git commit chain would be like this, there would be a dangling commit with nothing referring to it. So what Git does, it will create a merge commit, which will be a commit with 2 parents. But how does Git know how to combine the changes of the 2 commit chains? Well, that's kind of the next topic, the merge math, as I like to call it. Sometimes it's just simple like this. The different chains can easily be added, so plus A, plus B, and then in the other commit chain we have plus D, and in the other we replace A with F and add a C, so in the end we have BB, F, D, C. But okay, the commits can have a lot of changes, so let's look more into depth how Git handles this. Here we have 2 commits and a combination of multiple commits. But on the left hand we've added file X and made some changes in file Y. And on the right side we've added a file called file Z, and we also made some changes in file Y. Luckily, these changes were all done on different line numbers, so Git could just easily weave them together, just like a merger on the highway. But now, what if the changes were on the same line? Well, in that case, Git can't solve the merge. It has no clue what change should predominate the other change, so it will mark the change as being a conflict. So it say, please tell me how to solve this conflict. What should be the outcome of these changes? So it will go into the conflicted state and it will try to help us as good as possible. It will say, okay, well, we have a change from the head here and from the branch we currently are on. And we have some changes from the feature branch you want to merge. So please tell me what should be the outcome of this. In this case, we use some tool or do it manually, make your changes and tell Git, okay, this should be the outcome. You add the file, commit it, and everything is done. One tip, when there is a merge conflict, Git will pause the process. It will just wait until you've solved the conflicted files. So when you can't solve the issue or you don't feel like it, you can just always abort the merge process and Git will go back to the situation it was before you started the merge. So just to clarify, a merge commit is also just a regular commit, except it had 2 parents. So that's the difference with fast forward, because you won't see a fast forward in the Git history, you just move the branch pointer up into another commit. A merge commit is an actual commit, so you can also just undo it by resetting it, which is something I will talk about later. So if you've merged but are not happy with it, you can easily just undo it and make it like it never happened. So next subject is tags. A tag is just a label pointing to a specific commit. But unlike branches, they won't move when new commits are added. They will point to the same commit forever. So the branch will move with a new commit, and the tag will keep pointing to the same specific commit. So this is very useful for keeping track of releases and add some version number, for instance with semantic versioning. Or you want to remember when you started with a major refactoring or something. One very important thing is that if you create a tag for public usage, so when you want to share the tag with other people, for instance for releases and stuff, then you should create an annotated tag by adding the -a in the command. You should always do this. I have no idea why they haven't made this the default behavior of tags. The big difference is that when it will add metadata to the tag, so who created it and what time and date. If you don't do this, the tag will be lightweighted and it will only point to a commit with no information about who created it at what time. So please remind yourself to always do this and thank me someday. So up until this point, we've been talking everything was locally, but it's very useful to have a remote, something else to store your changes for backup or sharing your work with others. So a remote is a repository elsewhere, and elsewhere is outside your working copy. So it could be on GitLab, GitHub, Bitbucket, but it could also be your neighbor's PC or another folder on your own PC, or, well, there are lots of options. So how does this work? Well, hopefully you're now a little bit familiar with the commit chain with a branch and some commits. And you can add a reference to a remote by cloning or adding it. And the default name is origin. Just like the master branch earlier, or the main branch, this is just a default by Git. The remote could just easily be called foo or whatever. So what you do with your remote is you tell Git what remote you want to push and what branch. In this case, it will be origin, remote, and the main branch. In recent Git versions, you don't have to supply this information. By default, it will push to origin and use your current branch. So you can skip this information and just do a git push with the same result. What this does is it will update the current branch, or it will push the current branch state to the remote. So if you add a new commit and do a push, the remote will do a fast forward. And this is important to realize that the remote only wants to do a fast forward. It will never do a merge or anything. So now the other way around. Your remote has some changes by somebody else, but how does the local repository know there are changes compared to the remote? Well, there is a secret or a hidden branch called remotes, your remote name and your branch name. So in this case, it's remote origin main, which will represent the remote state. So when you do a git fetch, it will update all remote branches. So your remote branch will be fast forwarded. And then you can do a git merge, so your current branch will be fast forwarded as well. So this could become very tedious to do all the time, git fetch, git merge. So you could do also this all in once with a git pull. And this is kind of the same with the git push. You can supply which remote and which branch, but just like git push, you could also skip this information and it will default to origin and your current branch. But remember, git pull will always do a merge. So what will happen if two branches are not in sync? You've made some changes locally and there are some other changes on the remote. So it can't be easily be fast forwarded. So if you then do a git push, then you will get this message, which we've all seen and dislike every time we see it, but it's just Git explaining what's going on. The message is actually very clear. It says, it looks like the tip of your current branch is behind the remote counterpart, so you have to do a git pull. And what this means is that your current remote origin main is not pointing to the same commit as the main branch on the remote. So you have to do a git fetch to update the local remote branch, and that will result in this, that the remote's origin main will be pointing to the same commit as the remote. But now we want to have these changes into our main. So now we do a git merge. And this is just the same as with a local feature branch. Git will create a merge commit with two parents, and now the commit of the remotes is also in our main. And up until now, everything was still locally. So the remote is not updated, and therefore the remote's branch is still pointing to the remote commit. So when we do a git push, our local changes will be pushed to the remote. The remote can do a fast forward since we've added the merge commit. And then the locally remote's reference branch will also point to the same commit, the merge commit. So everything is in sync again. One pro tip, this will make some very ugly merge commits, especially if you have to do a pull a lot when a lot of people are contributing on the same branch, and every time Git has to make a new merge commit. So you can do this in a lot cleaner by doing a rebase, and I will explain this in a later slide. So let's talk about more advanced stuff and why it's good to keep your commits small. There are a couple of things we can do with our commits. For instance, we could do a revert, which will pick a specific commit and undo the changes. This will add a new commit in the history containing the opposite delta, so you can revert or roll back changes you've made previously. So how this works is, for instance, we have the current chain of commits, and we want to revert this commit where we replace the A for the E. So if we revert it, git revert and the hash, Git will add a new commit containing the opposite delta. So it will remove the E and add the A. Be aware that this will be a new commit in a commit chain. Another thing is that it doesn't have to be the last commit, it could be any commit. So we could also revert this specific commit, and this will add another commit on top of the commit chain where we remove the L. Be aware this will be another commit, so the original commit will still be in the history. And since a revert reverts a whole commit, it's useful to keep our commits small and focused so we can easily revert specific changes. And an example of the benefits of creating small focused commits is also the cherry pick. What cherry pick does is you pick a specific commit, one or more, and you apply these one by one on a different branch. Therefore, it's recommended to commit often and keep your commits as small as possible. Don't bundle all your changes into one big commit, but combine only the changes that are part of the same solution or problem. This way you can easily pick the commits and reapply them elsewhere. So how this works is, let's say you have two branches called main and develop, and you want to apply these commit B on the main branch. You could just manually copy paste the changes into your files, but that could be error prone, and often it is more convenient to apply the changes from your commit. So you have to make sure you are on the branch you want to apply it, and then you type git cherrypick with the commit hash, or multiple commits, and then Git will apply the changes from the commits on top of your current branch. And be aware, the commit hash of the new commit will not be the same, since it's a different commit chain with different parents and such. So the only thing that is applied is the delta of the commit. So let's talk about more advanced stuff like bisect. This is a very convenient way to determine what commit introduced an error. Very useful for when suddenly you encounter a bug but have no idea what caused it, or when something in your styling is suddenly wrong, your text has different font size or some margin is wrong, but you can't find easily what's causing it. In those cases, bisect is very useful. Git will use binary search method to aid you in your debug process. So you start a bisect with git bisect start. And then you have to give Git a range of commits, telling which commit is good and which commit is bad. So for instance, we say this commit is bad, or if it's the current commit, you can just say git bisect bad. You don't have to give a specific SHA. And then you have to tell Git what other commit is good. Often this is a production version of some other branch, so you could also pass in a tag, which in the end is just a pointer or reference to a commit. So now Git has a range, between A10B and F289, there was one commit that introduced some unwanted change. So Git will check out the commit in the middle of the range and will ask you if this commit is good or bad. So now you can look at the state of your project, you can run tests, do some manual checking in the browser or something. You could even automate this process by providing a script that runs on every bisect step. But I usually do this manually because most of the time when I need bisect, it's something visually that's wrong or some weird edge case. So I have to reproduce that by myself. So in this example, we will say this commit was good. So now Git will mark all commits up until this point as being good, and we'll go go into the middle again of the new range of the commits. So Git will check out the new in the middle commit, and you have to tell Git again if this commit is good or bad. And this process will go on and on. The range will decrease every time. If you say something is bad, the range will decrease the other way around. And eventually we'll end up with a commit where the bug was introduced. So in this example, we will say this commit was bad, and then Git will say, okay, I'm done searching, there were no commits left. So this commit is the first commit where something went wrong. And then you have to end the bisect process, because otherwise Git will stay in the bisect state until you end it. Because during a bisect, you can also check out your commits yourself or assign them as being good or bad, or do some cleanup, npm installs and stuff like that. So Git bisect, really useful. Next up, resetting. Well, Git reset has two functions. One is to reset the file from the staging area, like I showed previously. You've added a file and now you want to not include those changes in the commit, so you can do git reset with the file name. The other function of the reset is moving a branch, or to be more specific, to make it point to a different commit. Small side note, reset has a couple of options. The default is mixed, which will keep the working state as it is, but empty the staging area. You also have hard, which will also put the working state or working copy state in the state it was in the commit you point to. And you have soft, which will keep the working state or the working copy state and the staging area as it is. So for instance, you want to move the develop branch to some commit, to the same commit as the main branch. So you check out develop, so your head is pointing to it, and then you reset it to the commit SHA you want the branch to point at. And this is pretty interesting, because earlier we learned that a branch or a tag is a pointer to a commit. So if we can reset a branch to a specific commit SHA, we could also use a branch name or a tag as its input. So in this case, we could also done just git reset main test as hard. So why is this useful? Well, for instance, let's say you have a couple of commits locally, but you come to the conclusion that those commits are not needed anymore. So you remember that we have a secret hidden branch pointing to the commit of the remote called remote origin main. So we can just reset our branch to the remote origin main, which internally will point to a commit. So in the end, our main branch will also point to this commit, which will mean that those two commits won't have a branch pointing to them. So after approximately 90 days, they will be garbage collected. And this brings us to a very handy trick with reset that I use often. We've all been there. We started our branch or hotfix, and after some commits, we suddenly realized we've been committing on the wrong branch. For instance, we have a main branch and we made some commits, and then we think, oh no, this is a hotfix. I should have done this in a separate branch and not on the main branch. So what we easily can do now is to make a new branch called hotfix, some Jira number and some description, for instance. And so now we have two pointers to the same commit. And then we reset our main branch to the origin branch. Then we do a checkout of the new branch. And now we can continue easily in the new branch. No harm done. Very easy. Next up, Rebase. Well, what it actually does is move the starting point of a branch. Or to be put it differently, it will apply the commits of your branch starting from a different commit. So let's say you have a develop branch and a feature awesome branch. This is the commit that is the starting point of the featuring awesome branch. So let's say we have a couple of commits in develop and we want to have those changes into our feature awesome branch. We could do a git merge, but this will result into the ugly merge commit. And if you have to update your feature branch multiple times all the time, you'll have a lot of noisy merge commits in it. But there's a different solution, which will be more cleaner, and that is using git rebase. Remember this starting point? Git also remembers this, so you can tell Git that you want to apply the commits from our branch starting from a different starting point. So we do a git rebase develop. We say rebase the branch from the commit develop label points to. which then will kind of cut the connection between the starting point and the first commit of the branch. It will put the branch pointer aside for a moment, and then it will apply the commits one by one on top of the develop until all the commits are finished, and then it will have the branch point to the last commit again. One thing to realize is that the commit SHAs will be different since the parents changed and everything. So therefore it's best practice to do this only when with your own local branches. One other thing is that you can end up in a conflicted state while the commits are applied, since something can be changed on the same lines or in the same files. In this case, you need to resolve the conflict and then continue the rebase process and the commits, and then the next commit will be applied. This rebasing will provide a very clean solution for the ugly merges we had earlier with the git pull. For instance, the situation where you pulled the remote develop into your local and merge that with your local develop. You can also do a git fetch, and then instead of merging it, we can do a git fetch and then a git rebase. So we apply our local develop changes on top of these changes. So we have a very clean local commit chain, and this can easily be pushed to the remote where it will be fast forward as well. So no ugly merge commits on the remote because we had to update our local state and stuff. So we can do this by adding the -- rebase when we pull, or we can just add it in our local git configuration. So we will always use the rebase when we do a git pull. And another convenient thing is to add the rebase auto stash. So any uncommitted work won't be lost when we do a rebase. It will be stashed and unstashed when the rebase is finished. And personally, I think everybody should have this by default in their git configuration. It will make your git history so much cleaner and more readable, and it has no downsides because it only applies the changes you made locally compared with the remote version. So please do this and make all your coworkers and your future selves happier. So last couple tips and tricks. Let's talk about Reflog. This is actually a history Git keeps of all the actions you did. If you did a commit, a checkout of a branch, you did a rebase or anything you do, Git will log this. This is useful, for instance, for when you reset a branch and have some commits without a branch pointing to it. Those commits would eventually be garbage collected, but using the reflog, you can find them and add a branch to it. Or if you have rebased a local branch and have no remote branch as a reference, you can still undo this rebase actions using the reflog. Let me give you 2 quick examples what the reflog looks like. If you type git reflog, you'll see a long list starting from now and then going back in time. So here you see I rebased interactive a couple of times, and what I did, I picked a commit, I did a fix up, I did some regular commits, and here's another example where I moved between branches, did some commits and did some pulls. So you can refer to every point in the reflog by the hat, the curly braces with the number between it, like this. So the reflog is not something you'll need every day, and it's definitely not easy, or even it's pretty advanced and complicated to use, but just know of its existence and someday you might need it. Another one is amend. This way you can add something to your last commit. Only do this before you push, because otherwise your commit SHA will be different and Git will complain. But this can be useful for when you forgot to add a file or want to fix a small typo you made in your previous commit, or just want to change the commit message, or if you, for instance, forgot to add the test snapshot. Another tip is to check out your Git configuration. There are a lot of options there, for instance, how Git handles the pulls and rebases and stuff. But you can also set up some aliases here, so you don't have to type as much. You can add a couple of commands yourself. Last but not least, let's talk about force push. When you do a push with force, you will, as the name implies, will forcefully override the remote state with your local state. And this is something you sometimes need. For instance, when you rebase your feature branch and want to push it, Git will complain that you can't push since the remote branch pointer will point to a different commit. So in that case, you want to push forcefully. But in that case, always use force with lease. I will recommend that you never ever use --force, but always use the --force with lease. This is a kind of fail-safe mechanism where Git checks if your local remote origin is still pointing to the same commit as the remote. Because if the remote points to a different commit, it means someone else has made some changes in the meantime, and it would, well, if you would forcefully override that commit would be gone. And often when you do --force, you only want to override your own changes because of a rebase or an amend action. So please be aware of the existence of this option, and well, 99% of the times you can use --force with lease. Maybe sometimes you will actually need --force, but be aware when to do that. Well, at the end of this presentation, I have some links with useful sources to learn more about Git. The Atlassian page are very useful, explaining everything I just explained very clearly. The SCM book is the official book explaining everything Git related into depth. It goes into a lot of detail, but it's very useful to look stuff up. And last is the Git for ages 4 and up. It's an older presentation, but I've been recommending people all the time since it explains how Git works using some Git stories. And I really learned a lot from it. Well, hope you enjoyed this talk. See ya!